Welcome back. In this video, we will be discussing how to balance chemical equations. For example, the reaction of solid zinc with solid silver chloride to produce solid zinc chloride and solid silver. Knowing your chemical nomenclature will allow you to write the formulas of all reactants and products. Once you have written the correct formulas, you cannot change them. This means that you cannot change any subscripts because that will change the identity of the compound. Now that we know everything that is in our equation, you should notice that we do not have the same number of atoms of each element on both sides of the equation. There are 2 chloride ions in the products, but there is only 1 chloride ion in the reactants. So, how do we get 2 chlorides on the reactant side? We will add a stoichiometric coefficient. In the case of our reaction, we will need a 2 in front of the AgCl. This balances our chlorides, but as you can see, it makes the silver unbalanced. What can we do to fix this? We're going to add a coefficient of 2 in front of the silver in the products. Counting all elements, we now have the same number of atoms on each side of the reaction. We have 1 zinc, 2 chlorides, and 2 silvers. This is a successfully balanced equation. Let's try another example. Let's have aqueous potassium hydroxide reacting with aqueous solution of phosphoric acid in order to produce an aqueous solution of potassium phosphate and liquid water. Notice that the polyatomic ion of phosphate is in both the reactants and in the products. Identifying polyatomic ions that stay together will simplify your balancing equations. If you notice that a polyatomic ion does not break down, then you can keep it together and balance it as one piece on both sides of the reaction arrow. Now let's list all of our elements and polyatomic ions from both sides of the equation. We have potassium, oxygen, hydrogen, and our phosphate. Please notice that our hydroxide polyatomic ion is not readily seen in the same form on the product side, so we must count our hydrogens and oxygens separately. If we look at our equation, we have 1 phosphate on both sides of the equation, so that's nicely balanced with 1 and 1. If we look at our product side with the potassium phosphate, we have 3 potassiums, whereas we only have 1 potassium on the reactant side. In order to balance that, we need a coefficient of 3, giving us 3 potassiums on each side. Now if we look at this, our oxygens and hydrogens need to be balanced on both sides. If we look, we have 3 oxygens on the left. We have 1 oxygen currently on the right. And then we have 3 hydrogens from our potassium hydroxide and 3 hydrogens from our phosphoric acid. In order to balance this on the product side, for 3 oxygens and 6 hydrogens, we need a stoichiometric coefficient in front of our water. If we give this a value of 3, we now see that we have 6 hydrogens and 3 oxygens. Making sure to always check each of your elements on both sides of the equation as you finish to make sure that all of your elements are equally balanced. I'd like to do some more equations, but I seem to have run out of space on the board. There we go, that's better. Let's try another example. let's take C4, H10, O2, solid, and combust this with diatomic oxygen gas to produce gaseous carbon dioxide and water vapor. We will write out all of the elements on both sides of the equation as we did before, but in this example, we have to have an order of priority. We want to leave the atoms that show up in multiple products or reactants until the end. If we change the coefficient in the diatomic oxygen, that will affect both the carbon dioxide and the water. So the best place to start is the large reactant. It contains 4 carbon atoms, while the only product with carbon dioxide, contains only 1. So we'll need to add a coefficient of 4 in front of the CO2. This now gives us 4 carbons on both sides of the reaction arrow. There are 10 hydrogens in our C4H10O2 and 2 hydrogens from our water. In order to balance those, we need a coefficient of 5 to give us now 10 hydrogens on both sides. Now that we have completed 2 out of the 3 atoms, we need to balance the oxygen. There are a total of 8 oxygens from our carbon dioxide and 5 oxygens from our water, give us a total of 13 oxygens on the product side. We have a total of 4 oxygens, 2 from the diatomic and 2 from our C4H10O2 on the reactant side. In order to balance this, we need to put a coefficient of 11/2 in front of our diatomic oxygen. Thus, we will have 13 oxygen atoms on both sides. Clearly, this is not an optimal solution. How can we fix this without redoing all of our work? Well, 11/2 becomes a whole number when multiplied by 2. So if we multiply the entire equation by a factor of 2, we will have to take each coefficient and multiply them throughout. So we will have 2 C4H10O2 solid reacting with 11 O2 gas to create 8 carbon dioxide gas and 10 water vapor. Now that we have a total of 8 carbons, 20 hydrogens, 26 oxygens on both sides of the equation. We've maintained our balance and now have whole integer values for all of our stoichiometric coefficients. Let's do one more example. Let's do the reaction of calcium phosphate solid reacting with silicon dioxide solid and carbon solid to produce white phosphorus, P4, solid, plus calcium silicate, solid, and carbon monoxide gas. Our polyatomic anion phosphate does not stay together, so we're going to have to go element by element to balance this equation. Let's start with the phosphorus. If we look at our phosphorus, we have 4 phosphorus atoms on the product side, while we only have 2 on our reactant side. In order to balance this, we need to put a coefficient of 2 in front of our calcium phosphate. This will now give us 2 times 2 for a total of 4 phosphoruses. Now that phosphorus is balanced, we can move on to calcium. There are now a total of 6 calciums in the reactant, so a coefficient of 6 is placed in front of the calcium silicate. We now have a total of 6 calciums on both sides of the reaction. This has now caused an imbalance in the silicon. We have 6 on the product side, so putting a 6 in front of the silicon dioxide will now balance these as well. There are 2 elements left to balance, the oxygen and the carbon. Currently, there are 28 oxygen atoms on the reactant side. We have a total of 16 oxygens from our calcium phosphate and 12 from our silicon dioxide. This gives us a total number of 28 oxygens on the reactant side. If we look on the product side, we notice that we have a total of 18 oxygens from our calcium silicate and 1 oxygen from our carbon monoxide. In order to make these balance 28 with the reactant side, we need to put a coefficient of 10 in front of our carbon monoxide, giving us now 10 oxygens from here and a total of 28 on the product side. The last element to balance is carbon. We now have 10 carbons on the product side, so a coefficient of 10 needs to be put on the reactant side in front of the solid carbon reactant. This will give us a total of 10 carbon atoms on both sides. Again, when you are finished, make sure to check that all of your elements on both sides are completely balanced to confirm that your overall equation has successfully balanced. Balancing equations is one of the most critical skills in general chemistry because using a balanced chemical equation will help in topics such as stoichiometry, acid-base chemistry, thermodynamics, equilibrium, and much more.